Okay, so today we're going to finish up all these single one-step transformation problems looking at the stretches. So we have the horizontal and the vertical stretching and compressing. We might start to look at 6.3 part 3. I'm not sure. So we'll see what we get to. So the first type of stretch we're going to look at is the vertical stretch. Now, with sine and cosine, we have something we can talk about with the graph that's called the amplitude. And the amplitude of a sine or cosine graph is the measurement from the center line on the graph up to the peak. And since that center line goes right through the middle of the function, it should be the same distance from the center down to the minimum. Okay, but that's called the amplitude. Now, the amplitude measures the height of the wave. Okay? So it's measuring a distance. What kind of number does distance always have to be? Michael?
Positive.
Positive. So there's no such thing as a graph with negative amplitude. Okay. So amplitude, if I ask you for the amplitude of a graph, you would be giving me a positive number. So these are also the first kind of questions you're going to see that you actually don't have to do a full sketch in a table. If I just ask you, what is the amplitude of this graph? You'll just be able to write a number. You don't have to do a sketch. I might ask you to sketch after, but we're going to try a few problems by figuring out what the amplitude is without graphing it at all. Okay. And an amplitude change, okay, as you would expect, that's a vertical stretch. And a vertical stretch is when you multiply on the outside of the function. So you have a number in front of sine or cosine. If you want to know what the amplitude is, you take the absolute value of the number in front. Only time you take the absolute value is if I specifically ask you the question, what is the amplitude? If you are sketching, you don't take the absolute value of the number in the front. Because remember, when you're sketching, if you have a negative next to C, that negative is important. It does something. Anybody remember what a negative would do? Tim?
Flip.
Yeah, it would flip it. Okay? So then the negative would cause a flip. So the negative is important when you're sketching. But if you're asked the question, what is the height of the graph or what's the amplitude? It's the absolute value of the number in front. We already said that the amplitude is always a positive number. And amplitude changes stretch or compress the graph along the y-axis. And an amplitude change has to do, we can tie some of these things into sound. And I don't know if I don't think we did this yesterday. So let me bring something up. And this is going to be what's called an oscilloscope. And it takes a picture of, or it takes in sound, and it turns the sound into a picture that you can see. There's a little bit of a delay, but just the way it's set up. It doesn't look like anything nice and neat and organized because usually voice patterns are not. Right? Voice patterns have constantly changing volume. They have a constantly changing frequency. But if I were to make a constant sound, right, at the same frequency, like whistling, you would see a nice sine wave. And if I do it soft, you'll see the wave kind of small. And then if I try to get louder, you'll see the wave get bigger. So let me see if I can, I don't know if I can do that, but let me try. So. So you can see as I get louder, the wave got louder. I tried not to change the pitch, but with my mask on, it's hard to whistle. So that was a nice sine wave. Hopefully you could see it when it was quieter because it wasn't maxing out on the screen. But that's the effect of changing the amplitude. Okay, if you talk softer, you'll see a wave on the screen that's not going up and down as much. And then if I start to talk louder, you'll see the wave going up and down more, because it's a louder amplitude. All right, so we'll bring that back up when we do the next transformation, which is horizontal stretching and compressing. All right, so let's see if we can find the amplitude of that. All right, so what's the amplitude of 3 cosine x? Nick?
3.
3. Okay, so that's a question that you'll see on the test. So amplitude there is 3. Let's go down. How about the amplitude here? What's the amplitude of that one? Yep.
4/3.
4/3. Okay, there's other things happening there that we talked about yesterday. There is a phase shift by pi/2 radians to the left, and there's a vertical shift up 6. Those don't have anything to do with changing the amplitude. Okay. How about -2 sine x? What would be the amplitude of that one? Caleb?
2.
2. What would be the amplitude now? Still 2. Okay, that negative has no effect on the amplitude. All that does is affect a vertical reflection. Okay. So any question on finding amplitude? Okay, that's pretty straightforward. So let's start to think a little bit about what's going to happen. When you do an amplitude change, you're stretching and compressing the graph vertically. What values are not affected by stretching and compressing something vertically? So think about what's going to change and think about what wouldn't change. Okay, I want to know what's not affected. Yeah?
The x values.
The x values. Okay? So the x values are going to stay the same. Imagine taking a point and tripling its height. Think about what part of the coordinate you'd change. You'd change the y. You would not change the x. So the x's stay the same. And then to find the new y values, the calculation here is pretty simple. It's almost as easy as when we did the vertical shift. All we have to do is multiply the old y values by c. And remember, c is the factor of the vertical stretch. And you use c exactly the way it is. If it's a negative, use the negative, because that's going to cause the reflection as well. All right, so let's try an example. Okay, so first thing we'd have to do is identify what kind of transformation this is. It's multiplication in the front. That makes it a vertical stretch, okay, or a change in the amplitude of the graph. All right, so John, what values are going to stay the same?
The x values.
And can you tell me what my standard x values are?
They should be 0, pi/2, pi, 3 pi/2, and 2 pi.
And 2 pi. All right. And just off to the side, what I'll do is put my original y values for cosine. And Caleb, what are my original y values for cosine?
1, 0, -1, 0, 1.
1. All right. And now, Madison, what am I going to do to all those y values?
Multiply by 3.
Yeah, they're all going to get multiplied by 3. So I have 3, 0, -3, 0, 3. And there's your table. And since we're only doing problems that have single-step transformations, one column will always stay the same, one column will change. We're going to do multi-step soon. Okay, we'll get to that. All right, so now we have to set up our graph. What I usually do when I have a amplitude change, especially if the amplitude change starts to get really big, I scale my axes so I don't have to draw it that big. So what I'm going to do is I'm going to go by 3s on the y-axis. And then the x's I'm going to label using the values in that column. Right, so we got 0, pi over 2, pi, 3 pi over 2, and 2 pi. All right, and then plot your points. 3, 0, negative 3, 0, 3. Okay, and remember, just try to make it so it has that curvature that gives it the concavity. So there you go. It's okay. So basically, every amplitude change that I do looks, for cosine, will look exactly like that. Because if this problem said to do 5 cosine x, all I would do graphing-wise is change these two numbers. Now I have a graph of 5 cosine x. Okay, so that's why, if you notice, a lot of my graphs are going to look the same because I change the scale every problem I do. All right, any questions on that? Okay, let's try with a sine. And when you put a number less than 1 in front, what does that do? It's multiplying, but it's less than 1. Last time we were multiplying, but we were more than 1. Yep.
Compressive.
Yeah, that's really going to compress it. All right, so let's make our table. Maddie, what values are going to stay the same here?
The x.
The x's. So 0, pi over 2, pi, pi over 2, 2 pi. Lindsay, what are my y values, my original for sine?
0, 1, 0, negative 1, 0.
All right. And Annalise, we're going to take all of those and do what with them?
Multiply them by 1/2.
Multiply them by 1/2. All right, so we're going to have 0, 1/2, 0, negative 1/2, and 0. So I told you yesterday that we don't want to use any decimals. It'd be okay if you put 0.5 there and negative 0.5 there. When I say we're not using decimals, I'm more concerned about fractions that would have pi. Like for this, I don't want to see 0, 1.57, 3.14, and so on. Okay. But if you can write it as a decimal and it's an exact decimal, that's okay. Okay, questions on the table? All right, so I'm going to do the same type of scaling that I normally do. 0, 1/2, negative 1/2. Okay, I do need to label everything because if you don't put labels, then it's assumed you're going by ones. None of my tick marks here go by ones. All right, so 0, pi over 2, pi, 3 pi over 2, 2 pi. All right, and 0, 1/2, 0, negative 1/2, 0. 0, 1/2, 0, negative 1/2, 0. There you go. Okay. Any questions on that one? All right. What's going to happen here? We don't have to actually do the sketch. Maybe we'll just do the table on this one. John? Yeah, it's a vertical reflection. What's the amplitude of this graph? 1. There is no real change in amplitude, but you can treat it the same way arithmetic-wise like you would do an amplitude change. It's like you're multiplying all the y values by negative 1. So x's would stay the same. And the y values normally would be 1, 0, negative 1, 0, 1. Well, change the sign of all of them. So negative 1, 0, 1, 0, negative 1. And then you could do your sketch. Okay, any questions on that? So that's the third transformation. Okay, that's the vertical stretch, which is called an amplitude change. Last transformation. That's a period change. So a period change is just another name for a horizontal stretch or compression. Okay, but period change is when we stretch or compress horizontally. How do you recognize an equation as a period change? What operation do you generally look for, and where does it have to be? Michael?
Multiplication or division inside the parentheses.
Yep, we got to have multiplication or division inside. So if you had something like log of 2x, that's a horizontal, technically compression by a factor of 2. Remember, inside is always reversed. If you had a log of 1/3 x, that would also be a horizontal transformation, and that would be a stretch by a factor of 3. Okay? So it's basically the reciprocal of that. If you want to talk about it, like you could say that this is a stretch by 3. I guess you could say it as a double negative. You could say compress by 1/3. That's kind of weird though. That's like saying move down -2. Technically, down -2 would mean up, but that's more confusing to say it that way. So I would describe this as a stretch by a factor of 3 and a compression by a factor of 2. But again, there's other ways to say it. So the standard period for sine and cosine is 2 pi, and that's been the period for every problem we've done so far, because we have not stretched or compressed it horizontally. So remember, the period is the length of time it takes for you to travel along the x-axis and complete a full cycle. Beyond that length, you're going to be sketching something you've already sketched before. Okay, it's going to repeat itself. So period changes have the form of sine bx or cosine bx. If b is greater than 1, it will cause a compression. If b is between 0 and 1, it will cause a stretch. We're going to focus on examples specifically where b is greater than 0. We know what would happen if b was less than 0. It's a reflection. We're not going to look at that right now. So period change stretches and compresses the graph horizontally. Or you could say stretches and compresses along the x-axis. I just said that, and it's the same logic we've been using all year. If b is greater than 1, you get compression. If b is less than 1, but we're going to look at still greater than 0, so between 0 and 1, you get a stretch. All right, so let me show you an example on the calculator. So let's compare sine x to sine 3x. Is that 3 going to cause compression or stretch? Tim? Compression. It's going to compress. It's going to compress by a factor of 3. I guess you could also say stretch by 1/3, because if you stretch by a number less than 1, that really means compress. So when we look at sine 3x, you're going to notice that it's going to oscillate faster. Particularly, it's going to oscillate 3 times as fast because it's compressed by a factor of 3. And if we take, and just look at that, in the original, one cycle was from here to there. If you look at the graph in blue, that's one cycle. Now we did sine 3x, which means we should have 3 red cycles in the same span of time that we originally had 1. So let's check. So we got 1, 2, 3. And now, does anybody know what that would do in terms of a sound frequency? It doesn't have to do with volume. That's the amplitude. The blue wave and the red wave would have different sounds. Yeah?
Wouldn't it be higher pitch?
Yeah, it would control the pitch. So what we could do, let's do it, let's see. All right, so we looked at that, and that, and that. So what we want to look at now is how can we find the period of a graph. Okay? So this is a non-graphing problem, kind of like finding the amplitude. And the formula to find the period of a sine or cosine function is 2 pi divided by the number in front of x. This is the number you're multiplying by to change the period. So it's 2 pi divided by the stretch or compression factor. And what this tells you is the length of the cycle. So let's say here's your sine wave. And you did something to that graph to stretch or compress it. And you wanted to know, okay, I'm starting at 0. Where would I end for one cycle? That formula will tell you exactly where the first cycle ends, because it gives you the distance from here to here. All right, so think about what would happen in these examples. Okay, we're going to find the period of the following. Let's start with y equals sine 2x. Don't even think about the formula yet. You're multiplying by 2. Is that going to stretch the graph, or is it going to compress it? It's going to compress it. So what that means is the length of the cycle is going to compress. It's going to shorten. So it's going to become a smaller number. So let's figure out exactly what that number would be. So the formula for the period is 2 pi divided by what in this case? 2. So the new length of the period is now pi. If you want to think about it in degrees, we used to have to travel 360 degrees on the x-axis to get a full cycle. Now you only have to travel half that to get a full cycle, 180 degrees. All right, let's look at this one. Okay, 1/3, cosine 1/3 x. What's going to happen to the graph in this case?
Stretch.
It's going to stretch. So now the original cycle was 2 pi. If you stretch it, that's going to get bigger. How much bigger? Well, let's do it out and see. 2 pi divided by 1/3. What's 2 pi divided by 1/3? Yep.
6 pi.
6 pi. And if you flip and multiply, that's how we divide the fractions. The original period was 2 pi. This period is 6 pi. It definitely got bigger. It got 3 times as big. All right, let's do this one. What would be my, well, first of all, would that stretch or compress? That's going to compress. That's a number bigger than 1. It's 3.14. It's still going to compress it. And what would the new period be? 2. Because it would be 2 pi over 2. And I messed that up.
2 pi over pi.
2 pi over pi. And then you would get 2. And that's also going to make the quarter points of the cycle very easy to find. 0, half, 1, 1.5, 2. So it makes it very easy to find those 5 points. And that's the first kind of problem. If we did it out as a graph, your x values wouldn't have any pi's in them. We've always had pi. But if you scale it by a factor of pi, it cancels it out. We'll try one like that. How about this one? What would be the period here?
2 pi over 3.
Yeah, 2 pi over 3. There's all kinds of other stuff going on in there, but that's just to kind of distract you from the real important number. Vertical shift by a factor of 2, doesn't matter. Vertical stretch by a factor of 2 has nothing to do with the period. Only number you have to focus on is the 3. All right, so let's think about what's going to change and what's going to stay the same when we do the table. We're going to stretch and compress horizontally. Okay, so things are going to kind of look like this. So if you focus on a point as I'm stretching and compressing horizontally, what value is changing? The x value or the y value? Yep. The x values are changing. So that means when we make the table, the y's are going to stay the same. Now there's different ways to find the x's. I'm going to show you one particular way. And the way that I'm going to show you is to take all the original x values and divide them by b. Okay, that's what you're scaling them by. So we take the original x values and we divide them all by b. Not always the easiest way to do it. Sometimes it is, depends on the problem. But this is a way that works for what we're going to be doing soon, which is multi-step. Okay, so take the original x values and divide by b. Or, if you don't want to think of it that way, instead of dividing by b, what could you multiply by instead? Yep.
1.
You could think of it that way. If you don't want to think of dividing by b, think of multiplying by the reciprocal, 1 over b. I tend to think of it this way when I have a problem like this. Instead of taking a point and dividing by a fraction, I'll think of it as multiplying by the reciprocal. Okay, it makes it easier so we don't have fractions over fractions. All right, so let's look at this one. All right, so Nick, what values, well, first of all, what kind of transformation is that?
Horizontal stretch.
Yeah, that's one of our period changes. Okay, that's a horizontal stretch or compression. And what values are going to remain the same?
Y.
Y's. 0, 1, 0, -1, 0. Okay, if you're not sure where those are coming from, that's the notes from yesterday. Okay, let's take a look at our original x's. 0, pi over 2, pi, 3 pi over 2, 2 pi. And what am I going to do to all those x values?
Divide.
Yep, divide by what?
1/2.
Yep, you could divide them all by a half, or you could think of that as multiplied by 2. I'm going to think of it as multiplying by 2. So basically just double all the x's. 0, pi, 2 pi, 3 pi, 4 pi. We just multiplied everything by 2. That's it. And let's see if that makes sense. We multiplied by a number that was less than 1. That should cause a stretch, and it did. All right, so we're going to start at 0. The graph isn't going to look stretched out because I'm going to change my scale. Okay, if we tried to keep everything at the same scale, and we had a graph that really stretched out, I mean, we'd have to draw it huge. Okay, so we'll always change our scale. So pi, 2 pi, 3 pi, 4 pi. Technically, you don't need a label on the y-axis if you don't want to put this. I'll put it, just put it. And let's do the sketch. So 0, 1, 0. And that would have normally been where the cycle ended. 2 pi is the end of a normal cycle. We're only halfway, okay, because we doubled the cycle length. -1, back to 0. Any questions on that? Okay. Let's try this one. All right. So Mabel, what kind of transformation is that?
It's compression,
Which way?
horizontal.
Yeah, that's going to be a horizontal compression by a factor of 2. You could also say stretch by a half. And what values in my table, Tim, will stay the same?
The y.
Y's. And Michael, can you give me my y values for cosine?
1, 0, negative 1, 0, 1.
So we got those. Let's take the original x's. And Julie, what am I going to do to all my x values?
Divided by 2.
Yeah, divide by 2 or take half. Same thing. So John, can you tell me what I get when I divide all those by 2?
0 divided by 2 is 0. Power of 2 divided by 2 is pi over 4. And then that would be power of 2. And then that would be 3 pi over 4. The last one would just be pi.
Yep. And if you're looking at that and you're like, whoa, there's no pattern there. There is if you write everything with a denominator of 4. 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4. So there's a nice pattern. Okay, any question on that one? Now we just make our table. So these are all equally spaced. They're all 45 degrees apart. That's 0, 45, 90, 135, 180. So we can use those as our labels. Pi over 4, pi over 2, and plot our points. 1, 0, negative 1, 0, 1. Questions on that one? All right, so let's try one more. And this one, I think the x values are actually going to come out very nice. It looks like you have a pretty bad number in front of x at first, but let's see what happens. So this is another cosine. We just did cosine, so we already know the y values. We're going to take our x values. Pi over 2, pi, 3 pi over 2, 2 pi. And what am I going to do to all those x values? John?
You're going to divide them by pi over 3.
Divide them by pi over 3, or,
Multiply them by 1 over pi over 3.
which is?
So that would be 0.
Can you simplify 1 over pi over 3?
3 over pi.
Yeah, just 3 over pi. So let's multiply all these by 3 over pi. And the first one would be 0. Caleb, my second one?
3 over 2.
3 over 2. Or if you want to write that as a decimal, it's 1.5. 3. How about the next one?
0.
What is it? Yeah.
9/4.
Can you say it? What would it be as a decimal? 9.5 or 9 halves, which is 4.5. And what about the last one? 6. So the pattern here is the x values are going up by 1.5 each time. So this would be one if you don't want to label your tick marks. You don't have to. Let's just go by ones. You might need one more, I think. So we have the point 0, 1, 1.5, 0, 3, negative 1, 4.5, 0, and 6, 1. So about like that. So that's a, let's see, that's a little bit of a stretch. No, wait a minute, that's a little bit of a compression, just barely. Because you're multiplying by pi over 3. Right, that's like 3 point, I mean, if you divide pi by 3, it's just a little bigger than 1. So it's just barely a compression. And there's our sketch. Okay. Any question on that? Okay. Show the video first. All right, so the first part of the homework, and again, I'll make sure I post this video online so you can get those questions. We'll be graphing those 8. And again, make sure that you show the table. Okay, so I think most of those will be pretty quick. Right, but I can even put that back up at the end of class if we need to. All right, so the last part of 6.3, which again, we normally don't even break into its own section, is just looking at multi-transformations. There's a certain order that we always follow. It's the same order we've always done. Can anybody tell me what's the first transformation that you always look for? Tim?
Horizontal shift.
Okay, so first thing we look for, let's do an example with sine, would be horizontal shift. So you'd have a plus or a minus a inside. What's the next thing that you look for after that? Nick?
Horizontal stretch.
Horizontal stretch. That's where you multiply. I'll even put the letter off to the side here so you know which one is which. That's controlled by A. That's controlled by B. Okay, what's the next thing we look for after the horizontal stretch? Yeah?
Would it be the vertical shift?
Vertical shift is always last.
Vertical stretch.
So it's the vertical stretch, which is we call an amplitude change. That would be controlled by C. And then the last thing we look for is D, and that would be a vertical shift. Right, so we always process the transformations in that order. Now, technically, unless you're doing two transformations on the same axis, the order doesn't matter. Right? As long as, like, let's say you were doing a shift up and a shift left. It doesn't technically matter which one you do first because they are two separate axes. Shifting up has nothing to do with shifting left. But if you were going to do a shift left or right and a horizontal stretch or compression, then the order becomes important because you're doing two transformations on the same axis. Okay? Yep.
Could you remind me where the horizontal flip and vertical flip are?
Those would be B and C.
Okay.
So you can process, if you had a reflection, you can do it, we're not going to do it with B, but if B was negative, you could do it right in there. And then if C was negative, you could do it right in there. Yep. Okay, so let's try this one. What are the two transformations that we have here? Michael?
There's a horizontal shift and a vertical stretch.
Yes. Horizontal shift affects which axis?
X-axis.
X-axis. And vertical stretch affects which axis?
Y-axis.
They're two totally separate axes, so technically it doesn't matter which one you do first. Okay. They're not on the same axis. Let's do, let's process them both at the same time. I think we can handle that. So let's put our original x's over here. And what am I going to do to all those x values? Nick?
Subtract pi over 2.
Subtract pi over 2, because we want everything to shift to the left, so we want to make all these x's smaller. Can somebody tell me what you would get if you subtract pi over 2 from all of those? John?
You get negative pi over 2, and 0, pi over 2, and then pi, 3 pi over 2.
Perfect. So we just processed the phase shift. Now we have to do the vertical stretch. 0, 1, 0, negative 1, 0. Okay, what am I going to do to all my y values to deal with this vertical stretch by a factor of 2? Caleb?
Multiply them by 2.
Yeah, let's multiply them all by 2. So we end up with 0, 2, 0, negative 2, 0. So that's a multi-step transformation. Now we sketch it. All right, so let's see, we're going to need negative pi over 2 to, sorry, you probably said 3 pi over 2. I might have just not written that.
Yeah.
I don't know what I did. So negative pi over 2, 0. I don't know if you can see, my axes are a little bit bold. I know it's hard to see. There's my y-axis at 0. Pi over 2, pi, 3 pi over 2. And I'm going to go by 2's on my, my vertical. So let's make this 0. I'm just going to erase that so it doesn't look confusing. 2, negative 2. Right, so I just made a little grid. And now plot your points. Let's see. So negative pi over 2, 0. 0, 2. Pi over 2, 0. Pi negative 2. And 3 pi over 2, 0. And there's your sketch. Any questions on that? All right. Yes. John.
Oh, sorry. No, never mind.
All right, let's look at this one. So we've got 3 transformations, so we're definitely going to have 2 transformations affecting the same axis. No question. So now we have to think a little bit more about the order. Do I have a phase shift here? No, so we don't have to deal with that. Do I have a period change? Yes, I have a period change, and that's the only other thing that could affect the x-axis, because I don't have a phase shift, I have the period change, so let's process the period change, and then we'll be done with the x column. So 0, pi over 2, pi, 3 pi over 2, 2 pi. And what am I going to do to all those x values? Mabel? Divide by 2 or multiply by 1/2. So 0, I think we did this one. Pi over 4, pi over 2, 3 pi over 4, and pi. Yeah, I know we did that. They're all separated by 45 degrees. Now, we have 2 transformations affecting the y-axis. We have to do them in the right order. It's a ×3 and a +1. Think about PEMDAS. It makes a difference if you do +1 and then a ×3, or the other way around. Let's start with the original y's for cosine. Madison, what are my original y's for cosine?
1, 0, negative 1, 0, 1.
Good. Now, we have a vertical stretch and we have a vertical shift. Which one takes precedence? Which one do you have to do first? Nick?
The vertical stretch.
All right. How do you handle a vertical stretch? What's going to be the arithmetic we have to do?
You multiply by 3.
All right, so we're going to do a ×3. And then how would you handle the vertical shift? Yep. Add 1. That's the order we need to do it in. ×3, add 1. So ×3. And then add 1. need to move my grid. Okay, so let's go through our coordinates. Lindsay, can you tell me what my y values will be if I times 3 and then add 1?
4, 1, -2, 4, wait, 1, and then
And the last one?
4.
4. Okay, so 4, 1, -2, 1, 4. Thing that happens with cosine, a lot of times the order in the y column is the same forward and backwards. I guess you could do it. No, I don't think you could actually mess that up. It's always the same forward and backwards. I'm pretty sure. All right, so we've got, let's see, we got to go 4 to -4. So let's go 0, 4, -4. And don't need any labels in the negative for the x. I think I messed one up. 0, pi over 4, pi over 2, 3 pi over 4. Yeah. And pi. Sorry. Alright, so 0, 4. Go like this, it's easier. Pi over 4, 1. Okay, so 1, I'm just going to kind of estimate. Don't really have a good mark for that. Pi over 2, -2. 3 pi over 4, I'm at 1. And pi, I'm back at 4. All right. There's your sketch. Okay, any questions on that? All right, let me ask something here. What's the amplitude of that graph? 3? What's the period of that graph? Caleb? Pi. Now here's a question we're going to get into in a second. What's the maximum of that graph? 4. It's not always the same as the amplitude. It's because we did a vertical shift. So I want to point out there's a difference between the maximum value and the amplitude. Sometimes. In this case, there was. Does anybody have a question on how you would do one like that? You'd add the pi. There are 2 separate axes, so you could do either one first, technically. You'd add pi over 2 to all the x's, and you'd add 5 to all the y's. Okay, let's try this one. This is not a sketch on the by hand. It's more of a sketch on the calculator. So let's take a look at finding a complete graph. So finding a complete graph generally means you want to show at least one cycle. I would say show 2. You know, that's a good window. So let's type it in. So we've got 4 sine 3x. So let's clear that out. Type in 4 sine 3x, and I'm going to hit, well, let's go hit our window and think about that. Now, I want to do this in radians. So the first thing I'm going to do is I'm going to change my calculator to radians. What's going to be the period of this? John? 3 is part of the period, but the period will be a fraction. Yep.
Is it 2 pi over 3?
It's 2 pi over 3.
Oh.
So if I want to show 2 full cycles, I would need to double that. So the period is 2 pi over 3. By the way, you could do 360 over 3 if you were doing this in degrees, but we're doing it in radians. The 2 pi can be converted to degrees. So instead of doing 2 pi over 3 for the max, let's double it to 4 pi over 3. That'll show 2 full cycles. Now I got to think a little bit about the highest and lowest. I'm going to try -5 to 5, and you'll see that'll work fine. I also want to put a tick mark. I mean, the tick marks don't really matter I don't know, if you want to put one every 90 degrees, you could, but again, the tick mark is useless. I'm not going to use it at all. So I wouldn't worry about it. The important thing is, I hope I set this up to show exactly 2 full cycles, because I took the period and I doubled it for the x max. Perfect. So that's 2 cycles. Now, they want to know the domain, range, amplitude, and period. We already answered some of that. Mabel, what did you say the period was?
3 pi over 2 pi.
2 pi over 3. Okay, so we got that. Let's do the domain. What's the domain of this function? Yep. All real numbers. Every sine and cosine function is all real numbers. When we get into the tangents and the other ones, not so much. Okay, domain, all real numbers. What's the range in this case? Tim?
Or -4?
Including, not including?
Including.
Including. You do hit -4 and you do hit +4. In fact, how many times will you hit -4 and +4? Infinite. Yeah, you're going to hit it forever. Domain, range. Let's do amplitude. Okay, what's the amplitude here? Yeah. 4. And that's everything they wanted to know. So if it says find a complete graph, you do not have to sketch it by hand. Okay. Any questions on that one? Okay. We'll do that one, and then I think that'll be good. Okay, find a complete graph. Well, let's do the complete graph last. Let's see if we can figure out everything first, without a picture. What's the domain? Yep. All real numbers. Not too much thinking we have to do with that one. Okay, range. So there's 2 things I have to think about for range. Did I do a vertical stretch? If I did, take that into account. And then did I do a shift? If I did, take that into account. So what's my... It's not as complicated here. What's my range? Yep.
-3 to 3.
It will be -3 to 3. Now, let's say that there was a +2 on the end of that. What I would have done there is start with -3 to 3, and then I would have said, okay, up to, -1 to 5. Okay, I just would have added 2 to each of them. But it wasn't as complicated as that. Domain, range, period. What's the period in radians? Yep.
2 pi.
It's 2 pi. What would that be if I wanted it in degrees? Yeah.
360.
360. Good. Domain, range, period, and amplitude. What's the amplitude? Madison?
3.
Yep, 3. What if I did this? How would that affect the amplitude? Still be 3. If I put a negative there, how would that affect the period? Tim? Wouldn't affect it. How would it affect the range? Doesn't. If something goes from -3 to 3 and you flip it over, it's still -3 to 3. How would it affect the domain? It doesn't. So that negative doesn't do anything except do a reflection, which does not affect any of those values. Okay, just wanted to see if we could figure that out. Let's draw 3 cycles. I'm just choosing 3. So let's put in 3 sine of, let's see, x minus 1. All right, so we want to draw 3 cycles of that. So that means I need a window that is 6 pi wide. Okay. Now, if I start it at 0 and I go to 6 pi, what's going to happen is I'm going to cut off part of a cycle. Technically, it's okay. But see how I started mid-cycle of the sine? And that's because there was a shift by 1 unit. So if I shift my window 1 unit, then I can avoid that problem. So let's try making that a 19, and let's make that a 2. Oh, I didn't want it to clear all that though. What was it before, 6 pi? I wanted it to keep what it had. Just change it to a 2. So let's make it 19.85. Now it's changing things. That was originally a 0. So I still kept my window the same width. It was 0 to 6 pi. Now, I just shifted it 1 unit to the right. And what's going to happen when I graph it is now it
That's wild.
You changed the wrong.
changed the wrong thing. Well, X scale is not, I don't care what that's on. That's fine. So 0 to 6 pi plus 1. Yeah. 6 pi plus 1. And we want that at 1. There we go. So now, perfect. It's starting right at the normal position of sine, and I get 3 cycles. And so I'm just trying to show you how to manipulate the windows so you can make it so you don't cut a cycle off if that's what they had asked for. Okay. Any question on that? All right. So let me put up homework for tonight. So it's the 8 problems that I put up earlier. I'll write down. All right, so earlier in video, and not all of that. All right, let's see. Find the max and amplitude, so 2 through 4 should be okay. Find a complete graph in the domain, the range, and period. That's 7 through 10. 15 and 17 are sketching. And let's see. Find a viewing rectangle that shows exactly 1 period. Well, stop there. So the 8 graphs from earlier with tables, and then try those 10 or 11 questions from 346.